This is for Sac City Astronomy, Astronomy 320. The date, well, right now it's June 9th, but by the time this will be uploaded, it'll probably be June 10th. And so, the first thing we're looking at here is your Canvas page. I'm in student view, so just wanted to go through this real quick. Modules. Okay, most of you have taken the first day roll. Some of you haven't yet. It's going to be nice if everybody who I'm going to have on the roster took it, so I just know everybody's up to speed. Okay, this is online lecture that I just uploaded here a little bit ago. This is what we're going to be working through as we go through the video. And hold on, it's taking too long to load. Okay, wait. It was this is assignments, online documents. Okay, here, online lecture worksheets. This is what you want to download. And it's got questions on it that we're going to try to answer. We probably won't get all of them in this video because I don't want this video to go more than 40 minutes, but we'll get quite a few, hopefully. And so you want to download that, and then this is what you can type into. And then when you type in your answers, you can then send it back. This is in the under the assignments. It's 5 points, and it's not due till June 16th. Okay, so you would submit you write into it, you type into it, and then you would submit it here, and then Canvas will tell me that you turned it in. All right, so there's that, and then this is the PowerPoint that we are going to go over right now. And this might take a while to load. So anyway, I don't want to, let's see, wait till it loads. Okay, it's going to take too long to load, but it's this right here. This is the PowerPoint. This is the PowerPoint right here. Okay, so this is what you can download, and this is what we're going to go over right now. So if there are, that covers everything. Online lecture PowerPoint presentation. This is what's the syllabus, and then and then this is the online lecture. This is where you turn the online lecture into, and this is where you download the online lecture. This is the first one, so it'll be 001, 002, and like that. Okay, now here's our textbook that we'll be using. I think it's right here. So we start off the nature of astronomy, and basically it talks about what astronomy is exactly. Now, first of all, it is not astrology. People email me, say they want to add my astrology class. Astrology is a pseudoscience. It's a fake science. There's no way to support any theory that comes up in astrology. There's no way to repeat stuff. This is astronomy. Okay, this is a science. There's a big difference. Okay, so we're studying all the celestial spheres, the solar system, the galaxies, the stars, all of that good stuff. We're studying how the universe basically works, is what this is about in astronomy. Okay, so the first chat you can see is very short. We go on to the next. And the nature of science. Okay, what exactly is science? So if we go to our PowerPoint demonstration, what is science? Okay, you start with an observation. Obviously, going back to ancient history, it was all about starting with some sort of observation, whether it be lightning causes fire or this rock rolled down the hill. Okay, why did the rock roll down the hill? So ancient people were seeing things in their everyday life and making observations, and then basically nobody really studied too deeply what was going on here until the ancient Greeks. The ancient Greeks, like 2,000 some odd years ago, were the first to actually try to explain things. They were the first to try to explain. So before that, it would be Atlas holding up the earth, or they had some Greek god who was pulling the sun across the sky. Okay, they weren't happy with those kind of explanations. They wanted actual explanations. So they went ahead and they would actually propose a theory for why things did what they did. Now, the thing about the Greeks were that they were very good at making observations and then proposing theories based on those observations. What they didn't like to do was experimentation. They didn't do experiments. One second. Okay, so they would make these observations. They would come up with some explanation, and a lot of their explanations were just plain wrong. Okay, they didn't take a lot of stuff into account. One of their arguments that the reason the Earth was stationary at the center of the universe is because if the Earth was not stationary, there would be a constant wind. In other words, we would be moving through whatever was out there, okay? And so there'd always be a constant wind. What they didn't realize was the atmosphere the Earth has moves with the Earth, okay? And they didn't realize once you got past a certain distance, the atmosphere disappeared. So because they lacked a lot of knowledge about things, they came to a lot of wrong conclusions. But the idea is what we want to do now, okay, is to actually go through, use experimentation to try to test the explanation or the theory. Okay, and if flaws are found in the explanation or the theory, then it must be modified. But for centuries and centuries, people did really not really go into it. They just noticed things, they wondered maybe a little bit, but then they'd go on with their life. So then it took, actually we can do this. So then it took Galileo to finally say, wait a second, you know what, the Greeks believed that he dropped two objects. One has way more mass than the other one has. The one with the more mass would fall faster than the one with the less mass. They just said that's the way the universe is, take it, believe it, whatever, move on. Well then, Galileo comes along and he says, well, is that true? Why don't we try it out? So Galileo probably did not actually go to the Leaning Tower of Pisa to do this experiment. This is something like, George Washington probably did not really chop down the cherry tree. An apple probably did not really fall on Sir Isaac Newton's head and cause him to come up with all these mathematical laws and physical laws. So, but he did roll stuff down planks. He did do things with experiments with different masses, and he discovered that this was not true. The ancient Greeks believed this was true. The Greeks believed in observation and logic, but not experimentation. They never went out and did it. And Galileo says, hey, I'm going to go out and try it. And then he tried it, and he saw this was not true. You take two masses, one big, a bowling ball and a baseball, for example, you drop them from a great height, they will basically hit the ground at the same time. If there's no air resistance, they'd hit the ground at exactly the same time. Okay, so Galileo finally put this thing to the test. Okay, there's also other models that came up. There was the Ptolemy model for the solar system where Earth was at the center. And again, his argument was Earth had to be stationary. Everything else had to be moving around the Earth because otherwise we'd feel a constant wind. And a lot of times you go outside, you don't feel a wind. Earth must not be moving. Okay, so they didn't realize the atmosphere moves with the Earth. And we move with the Earth. Okay, so this was the geocentric model of the universe. The first theory to try to explain the design of the solar system placed the Earth at the center. All other celestial bodies orbited the sun. All other orbital. Oops, this is wrong. I've already uploaded it, but hold on. Okay, if I remember, I'm going to re-upload this guy here. If you've already downloaded it because you saw it on there, I made a change here. It's supposed to be all of the celestial bodies orbit the Earth. This was the geocentric model of the universe. Okay, let's go reconnect with where the book is. Okay, so it talks about what science is here. Hypothesis goes into great detail, and so on. The next chapter. This is the laws of nature. And so basically what science tries to do is tries to make sense of everything. So you come up with an observation, you try to come up with some theory to try to explain that observation, and then you try to do experiments which test the theory. Okay, you try to do experiments to test the theory. And sooner or later you can come up with laws that govern the universe. So you've got Sir Isaac Newton's laws of motion, you've got the universal law of gravitation, you've got all sorts of laws out there that do a good job of explaining the way the universe works. Okay, you got Einstein's theory of relativity, you've got quantum mechanics, you've got a whole slew of things that were basically made by observation and then trying to explain it by hypotenuse, a theory, and then you test the theory, and and you have to test it. It has to be very testable. It has to be repeatable. It can't be, that's why UFOs. People say, why don't scientists study aliens from outer space? Well, there's nothing to study. You've got somebody claiming they got kidnapped by aliens. How do they prove it? They can't. They never have been able to. So that's not, science doesn't want that. Science wants to be able to observe and then repeat and make an experiment. Somebody in a lab in Germany can do an experiment. Somebody in a lab in Sacramento can do the same experiment and get the same results as somebody in a lab in Argentina and somebody in a lab in Japan or Thailand or Saudi Arabia or the Congo can do the same experiment and get the same results. You just have to read what the other one did. That's what science likes. It's repeatable. It's a law of nature. It explains how nature works. Okay, now let's go. We got to check out the. So, what was believed about falling objects of different masses before Galileo's experiments? Well, according to the Greeks, the the bigger mass would fall faster than the smaller mass. Okay, so you just type in there, bigger masses fell faster. Okay, what do we know now about falling objects of different masses thanks to Galileo? That they fall at the same rate. Now you say, well, I drop a penny and a feather, the penny hits the ground fat before the feather does. That's because of air resistance. If you could put them in a vacuum, then you would be able to actually see them fall at the same rate, and I just got an idea. Okay, I just got an idea for a video that I just thought of. So this video here I'm gonna reload this. So as soon as I'm done with this video, I'll reload the PowerPoint. I'll reload this right here. But there's the video. I got it up right here. I don't want to take too much time watching it. But it's an astronaut on the moon. He's got a hammer and a feather.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to be appropriate.
I'm trying to save time here.
They'll hit the ground at the same They'll hit the ground at the same time. How about that?
Okay, so I'm gonna reload this, and you can just click on here, and you can go and watch it. Maybe I'll even put it in the PowerPoint since I'm going to reload the PowerPoint. All right, so that's what we found out from Galileo. What did the theory of a geocentric universe propose? That's the one we talked about just now. We were talking about it. It's the one that said that. Where is it? There it is. Okay, it says that the Earth is the center of the universe and everything else orbits the Earth. I corrected it. We now know that that's not right, that the sun's the center of the solar system and the universe does not orbit around the sun. Okay, so we keep getting demoted. First, we're the center of the universe. Then, well, no, we orbit the sun like everything else in our solar system, but our sun must be the center of the universe. Nope, not even close. Okay, so we keep getting demoted. So scientific notation, you're not going to be asked to do any problems or any calculations where you got to use scientific notation, but you're going to see scientific notation in the book. The book's going to use a lot of scientific notation. So, a million here, you see a million there, that's times 10 to the 6th. So what you would just do is write 1 times 10 to the 6th. That saves you a lot of writing. Or you could write it as a meg. M stands for 10 to the 6th. So 101.5 megahertz, that means 101.5 million hertz on your FM dial, for example. Then 1,000 is a kilometer, for example. Then let's go down to the small ones. So you got micro, that's 10 to the minus 6, millis 10 to the minus 3, 46 milliliters, 5 micro, I can't read what I have there, micro something, micrometers maybe, and then nanometers. Okay, wavelengths. When we get into wavelengths, you'll be seeing a lot of micrometers and nanometers and even picometers at times. Okay, so just be aware of scientific notation and how it works, because the book is going to use it, because the book is the one that brought it up. Because the book's got it right numbers. See, we're in the numbers. So you talk about this vast number of numbers, 1.34 times 10 to the 16th kilometers. Okay, you don't want to have to write that out with 13400000000 because that becomes clunky and it's a pain in the rear. Okay. So the next page, or the next section, consequences of light time travel. Okay, so the universe is vast and old. What kind of distances are we talking about? If measured in units we are used to, such as miles and kilometers, the numbers would be enormous. So instead what we talk about is something called a light year. A light year is the distance that light travels in 1 year. Okay, so it is not a unit of time. Probably be a multiple choice question. We'll say light is a unit of time, or unit of distance, or unit of mass, or unit of force, or whatever. It's a unit of distance. People see the light year, they think, oh, it must be a time thing. No, it's the distance that light travels in a single year. The speed of light is 186,000 miles per second. So light travels 186,000 miles in a single second. Therefore, light, 186,000 miles is equal to 1 light second. So 186,000 miles is equal to 1 light second. So let's try to wrap our brain around this. Okay, I've got Sac State here because the last time I taught astronomy and I used this, I was at Sac State. So between Sac State University and Placerville, that's 30 miles. You are at Sac State with a laser and a mirror. Your friend is in Placerville with a mirror. So you got a direct line of sight to each other. Maybe you're both high up and maybe through a telescope you can kind of see each other or whatever. Okay, so you point your laser at your friend in Placerville. Your friend uses their mirror to reflect the light back to you. You reflect the light back towards your friend. Okay, so it's going back and forth here, and so on and so on. How many times will the light beam bounce back and forth between Sac State and Placerville in 1 second? Well, you take the 186,000 miles per second divided by 30 miles, because if it was 30 miles per second, it would go once. But then if it's 60, it would go twice. So all you do is take the velocity, divide it by the distance, we would get 62,000 times in 1 second. So light would bounce back and forth 6,200 times. It would make 3,100 round trips in a single second. The time it takes you to say 1 Mississippi, light would have traveled back and forth between Sacramento and Placerville 62,000 times. That distance, 62,000 times the distance, 62,000 times between Sacramento and Placerville, that's called 1 light second. That's a light second, okay? So therefore 62,000 times the distance between Sac State and Placerville is 1 light second. The distance that light travels in 1 second. Okay, now let us try to wrap our brain around what a light year is. We have some feel for the distance of a light second. The same number of times light will bounce back and forth over a distance of 30 miles, 6,200 times. It's about the same as the number of seconds in 1 hour and 45 minutes. A light year is the distance light travels in 1 year. There are 31,536,000 seconds in a year. So 31 million, I think I'm saying that right, 31,536,000 seconds in 1 year. So that many times, okay, and you know how far light travels in 1 second. You got kind of an idea. You know what 6,200 is. You kind of know the distance between Sacramento and Placerville, probably driven it sometimes. So this gives you an idea of what a light year would be, how huge that distance would be. Okay, and then I've got a YouTube video you can watch here. And so it's just about distances. I checked it out earlier. Let's see if I can see it. Okay, so we're not going to watch the whole thing, but you've got a link to it so you can watch it. So this guy just talks about, okay, it's taking too long to open.
Light
So just real quick.
But just how fast?
And you can see he's going through all the different, oh, this was so much faster earlier.
The human scale.
So either talk about light
Quite
minute.
small compared to the size of our solar system.
And so basically, you can watch this at your own leisure. So let's go back to our PowerPoint. Okay, so distances. So here we've got, this is that one, distances. All right, so the moon is 1.28 light seconds away. So it takes light from the moon to reach the Earth in 1.28 seconds. Okay. Light from the sun is 8.32 light minutes away. Okay, so it takes light from the sun 8.32 minutes to reach the Earth. Okay, at closest, Jupiter is 32.7 light minutes away. Okay, at farthest, and this is relative to the Earth, not to the sun, because sometimes we're on the same side in our orbit as Jupiter, and other times we're on the opposite side as Jupiter. Okay, Neptune. Now we got to go from minutes to hours. Neptune, it takes light from Neptune about 4 hours, about a little over 4 hours to reach the Earth. And then the nearest star is 1.22 light years away. So there is no star. This is Proxima Centauri. This is the closest star. I think it and Barnard star are the two closest stars to us. Okay, and it's still 6.22 light years away. So whatever you were doing, 4.22. Whatever you were doing 4.22 years ago, that's when this light started towards the Earth. That's when it emerged from this star and started towards the Earth. Sirius, this is the brightest star in the sky. It's called the Dog Star. It's 8.6 light years away. Polaris, the North Star, okay, it's 433 light years away. The light you see from Polaris started towards the Earth in, I think it's going to be 1587 now. I didn't update. Well, can I update it now? Here, I'm giving you the new one. Okay, so this was written last year. Okay, Galileo and Shakespeare will be about, I guess they'd be 23 now. Kepler was about 16 years old. So Galileo, so science is just, when you see light from Polaris, that light started towards Earth before we had modern science, because Galileo is called the father of modern science. And he was only 23 years old at the time, just starting on doing what he was going to do to make all these observations and theories and so on. Betelgeuse is 642.5 light years away. Betelgeuse is believed to be a red giant, meaning that it's close to maybe going supernova. If Betelgeuse goes supernova in our lifetime, and that's really close, and astronomically, that's very, very close. It would be spectacular. It would blow up, and if it happens in our lifetime, wow, that'd be something everybody would be talking about for a long, forever. Okay, then we've got the Andromeda Galaxy. That's the nearest galaxy. Another wrong thing here. It's 2.537 million light years away. So when you look at this galaxy here, and you can see it with the naked eye, just barely. When you look at it from Earth, you're looking at something that's 2.537 million light years away. Okay, I'm going to try to keep this. So let's stop here for now. Wait, what happened here? Over here. What's next? Okay, held and vast. Okay, so we'll start here tomorrow. Okay, let's look at our questions over here. Okay, so what is the theory of Okay, that's the one where they put the Earth at the center of the universe. Okay, what is a light year? It's the distance that light travels in 1 year. Okay, we didn't really list the planets in order of their distance from the sun, because that's coming up. We'll get to that. Just happen to have it out of order. How old is the universe? Okay, that's kind of where we're stopping now. Okay, what is the distance to the moon in light seconds? Okay, you got these. You got answers for these guys. We just went through this. Just get a general sense that when we talk about the moon, we're talking about light seconds. We're talking about the sun and Jupiter. We're talking about light minutes. We're talking about Neptune. We get further out. We're talking about light hours. Polaris, now we're talking about light years. And for Andromeda, we're talking about millions of light years. Oh, how old is the universe? I got that twice. Okay, so I think these are all the questions I'm going to have from Chapter 1. And we'll finish this off tomorrow. We still got to go through some of this other stuff here. Okay, so let me, I got, there is Andromeda, the Andromeda Galaxy in Stellarium, okay? And you can see its distance is 2.538 million, that's an M for million, light years away. Okay, let me call it quits for now. Maybe I'll be able to put up another one tomorrow, another one of these videos tomorrow. I got to work on my lab. I got a lab I got to finish off, so I'm going to work on that. So good night, and I think I'll probably try to post another video tomorrow. So see you later.